let's repeat rapidly what I taught you generally about p-values and hypothesis testing. I'll do that rapid. All repetition. We do a hypothesis test when we decide against a null hypothesis using the data. Decide whether or not we believe the null hypothesis using our sampled data. We reject if the p-value is small. We do not reject. Sometimes we allow ourselves to call that accept when we do not have a small p-value. Usually, we have to agree what small or large is. 5% is the mostly used global level, but anyone are free to choose other levels in their mutual contracts they do in whatever endeavor they are using hypothesis testing. We say that's the wording that something is statistically significant if the p-value is small. The steps are the following. We need to formulate hypothesis and make the choice. In principle, as I say, it's part of the contract with what we do. The global default contract is 5% if we don't state otherwise. We use the data and somehow compare data with hypothesis. Common sense, I think. Having done that, we can either find the p-value by looking into the right distribution for the test statistic that we are looking at, to quantifying by probability how far away from the null that the data really is. So if it's really far away, we say it's unlikely far away. The p-value becomes small when the data is far away from the null, which would lead us to reject the null if we are far away from the null with the data we have. I'm repeating myself again and again and again and again and again. Or we can alternatively, if we want, use the critical value approach, where we do not necessarily find the p-value, but if we know we're going to use a t-distribution with 17 degrees of freedom because I had 18 observations in my data set, I can go check the t-distribution beforehand and find the critical value. How large should the test statistic be to be far away from the null? I can find that in the distribution, and I call that the critical value. And then I just see, am I far away like this or not? That would be, in a way, the same thing, but just without actually giving the p-value. The nice thing about p-values are we can interpret a bit like this. Really small p-values, in a way you could say this, the thing about p-values, small p-values we allow ourselves to use for interpretation, right? The smaller, the more clear evidence we have. Large p-values, and large meaning beyond 10%, we never interpret the size of those. That's meaningless. It's a bit asymmetrical here. But it's to save you from making mistakes in their future life. It's a small p-values. P-values are only interesting when they become small. When they're not small, they're not really interesting. And we shouldn't use them for any kind of interpretation at all in their own rights. But small p-values are interesting. Formally speaking, across any situation that you will meet in your life, a p-value expresses the probability of seeing something even more extreme that I actually saw. It can be a bit tricky to understand this probability. It's a scenario-based probability, saying, what if the null is true? And then I take my data and say, what would the probability to be this far away from the null, or even further away? Even that extreme or even more extreme. That is a probability that evaluates how far away from the null my data really is. So it's kind of an evidence. It's a local data evidence against the null. It's not a long-term probability that we can use for any predictions of the future. It's a data-based evidence measure. It's a bit tricky and a bit philosophical to really go into. As I told you, many people are struggling with what these things really mean. For us, it's just an evidence of how far away from the null we are. And small p-values is large evidence against the null, right? And we have the link between our two tools, the confidence interval and the hypothesis testing. That is sort of, if you see think that it's a bit too much to even state a theorem because in your minds it was pretty clear already, then it's fine. But actually it is worthwhile to emphasize that doing hypothesis testing by the critical value method in a way is exactly the same as finding the confidence interval and observing whether my null is within the confidence interval or not, right? So the confidence interval has this, in fact, new interpretation if you want to be very specific about it. First day we learned of confidence interval, it was some random method, interval method that in the long run hits the true value 95% of the time if it's a 95% confidence interval. The other way of thinking of a confidence interval is it gives you those potential values for your phenomenon, for your system, for the mean of your phenomenon that you allow yourself to accept or believe in, accept as plausible values based on hypothesis testing idea. So hypothesis testing, confidence intervals are each other's sort of supplements, analogies, they go hand in hand if you want. That was the recap. Let's see how it goes. T-statistic is numerically smaller than the critical value. The only good thing to say about this is, now my wife is going to say, what did you do now? I went into a door again. The only good news is that we're only halfway through. And if I may give you a bit of credit, of course it's maybe slightly vague to ask the question like this. But nevertheless, small t-test statistic, numerically small, means they are close to zero, means that we do not have an indication of any difference. That's how your intuition should say. Small t statistics is because a hypothesis and some data is close to each other, right? When these are close to each other, we have not proven significance. We have not rejected the null, right? We did not find significance. We must accept the null because data and hypotheses are close to each other. Good job there. Now to the new thing of